So we have been looking at frequency estimations for last few days. So we'll continue to do that, and let's see. So if you notice that even the so frequency estimates. Okay. So the first algorithm we saw was this Mishra-Grice algorithm, which was quite great because you just take order k counters. But the problem with this algorithm is that it cannot combine if the data are coming from different sources. So it's like just one data, one sequence, then this is perfectly fine. But and you need to go through two passes to get an estimate. Like if you are saying this is, I mean, you can get an estimate on each of these things fi tilde, but you will not be able to say that, hey, in one pass these are the guys which are heavy hitters or something. So, but if I just wanted to get an estimate on each number, then that gives a very good estimates anyway, because that was an additive estimate for each. So what we proved is that fi hat was less than equal to fi, and it is fi at least m over k plus 1, where m was the data. But this cannot support deletions and things like that, and that is why people move to doing different ways to do frequency estimation. So basically this is what is called point query actually. So what you get, this is what is called point query. Okay. So the second data structure or second algorithm which we saw yesterday before we went, what is called count min sketch. Okay. So we will try to go through this once again and try to see several applications for count min sketch before we move forward and do something else. Okay. So as I told you, it takes two things, a W and a D. Okay. And what we had was that we had H1, H2 dot HD, like D are like our pairwise independent hash functions okay, from N to W. 1 to W. Okay. So you have W buckets, and the objects which are coming are in the range from 1 to N, and there are W buckets, and there are like D objects which are sending things to. And our algorithm was, while stream is not empty, what did we do, right? If my current is like some update is like IT and some delta D, means it tells you an index which where I want to make modification by delta T, okay, is the current item, then what did we do? So then we did for L equal to 1 to D, right, we are maintaining this counter which is indexed by which hash functions you are, and what we did is that, okay, fine, HL, so let's go to the Lth hash function, look at what this IT is, right, map to, okay, and what did we do to this counter? We just updated this counter by delta T. Okay. This is exactly what we did, and this was and while. And what did we return? So for I equal to 1 to N, right, for I equal to 1 to N, set xi tilde is equal to min over L equal to 1 to D, okay, and what did we do? C L of Hi. So this was a whole our algorithm. This is what count-min algorithm was. We had d hash functions. Okay, so think of this as like a rectangular box. Okay, this is like a d cross w box, right? So each row, think of them that uh, they are indexed by my hash functions h1, h2, hd, right? Now, and here is like 1, 2, each of these are buckets. So when a new item comes, I look at which place h1 goes, and so h1 might be sending this item it. So given, so when it comes, what we do? Oh, we look at h1 which location I2 it. So maybe this is the location where it sends, where h1 sends it to. This is the location someone sends. This is, and what this algorithm does is that, okay, for all this places, whatever it is, you add delta t to. This is precisely what the algorithm is doing. Okay, and the hope was that by doing this, like these hash functions are good enough that they spread the big hitters all around the places, and other things which goes into are the error which goes into is not too much. Okay, so we managed to prove. Okay, so now if in this setting, if you look at in this setting, then what does CLJ counts? If I say this, what does this counts? This is basically sum over what? All xi with the, what is the property of this? All I such that HL of j is I. What's other way around? No, HL of I is j. So all those items which are sent to jth location by my lth hash function. Okay, so this is basically what this guy is summing up to. Okay, and then we did our estimations. Okay, so as I told you, the idea is that we expect that other error to each of the buckets which where my heavy hitters has gone is less. Okay, so we'll come back to the heavy hitters, but currently what this returns you what is called point queries. Like for each point I'm giving an estimate, like for each of them. But for to solve heavy hitter, this is not solving my heavy hitter problem, right? For heavy hitter problem, I want more than something to be outputted and things of this nature. So we'll get to that. So what I have given you algorithm is for the point query. Okay. Now what did we manage to show? So this is the lemma which we showed yesterday. So let's write down the lemma because we will apply that lemma in different settings. Let d equal to omega log 1 over delta, okay, and w is greater than 2 over epsilon, okay. Then for fixed I in n, 1 to n, okay. Then for fixed I in n, what can we say first of all? Xi is less than equal to xi tilde, because this is always an overestimate because you might have some error, so this is correct. And we proved that probability that xi is more than xi tilde is greater than equal to xi plus epsilon times 1 norm of x, okay, is less than delta. So this is what we proved for if you have that many hash functions and with this range, then you can prove that this particular point is within this range, okay. And we said that if you wanted to succeed for all the points at the simultaneously, right, then you need to multiply, you need to have more than log 1 over delta function. So you will have log 1 over delta times some log n inside. Okay. So what does this tells us? This tells us that, so how much space usage is here? So space usage is, right? So space usage is roughly how many counters we have, right? We have dw counters, d times w counters, right? This is why this matrix is useful for thing, right? There are d into w counters. So number of counters is like roughly order log 1 over delta times epsilon. Okay, and hence how many bits does it take? You just multiply with log m, because there are m items which are going to come. So number of bits these counters will take is like order log 1 over delta over epsilon times log m. Again, we are doing only all this analysis for just one counter, like that. Oh, what, like not one counter, like one index. What is the probability that some particular index we have a good estimate? Okay, so this is what we managed to show, and of course we also have to multiply with number of. So how much does this hash functions takes, right? So hash functions will take how much? There are d hash functions, so it is going to take d time amount of space it takes to store each hash function, which is basically like 2 into log of w. Okay, so 2 times log of w, so which is like big O of d is like log 1 over delta times 2 goes into big O, and what is log of w is like log of 1 over delta, right? Hmm? Sorry, so log over epsilon, 2 by epsilon, right? So log over 1 over epsilon, which is nothing compared to this. Okay. And how did we go about this proof? So we to prove this, we all said, okay, let's fix some L, and let HL is the bucket that HL has as I to. Okay, so let's fix some bucket. Okay, fix some bucket, or no, fix some hash function. Let's say L. So I have fixed now hash one of the hash functions L, and suppose what is HLI will denote then is the bucket HL has I2. And then we said, okay, let's take this random variable. What was the random variable ZL we took? Was basically the counter, because if you notice in this whole algorithm, these counters are my random variable. They are something which will keep, which is a random object, right? So this is like C times so this is what I defined ZL to be, okay, is the counter value that I has to, right? That is a random variable, right? Okay, so what did we manage to get expectation of ZL? So we computed expectation of ZL, and we said, hey, this is equal to xi plus summation all those I not equal to I prime, things are hashed and blah blah blah, and then we use the fact that we are working with pairwise hash function to bound that expectation of ZL is xi plus summation I not equal to I prime 1 over w, right, I not equal to I prime xi prime times w. What? What?
There should be an index for I as well, right?
That is xi there, no?
No, for ZL. ZIL or something.
What?
ZIL or something like that.
This is what I'm trying to define at this point of time, where I don't need anything. big deal. Look, all these CW random variable, they behave like very similar, so I just fixed one. Okay. And because of our selection, we said that this is nothing but xi plus epsilon times mod x by 2. Okay. And then we applied Markov to which one? We applied Markov to, don't apply to this, you apply Markov to ZL minus xi, right? And just by Markov we said that probability that ZL minus xi is greater than or equal to epsilon times 1 norm of x is how much? Is less than half. Okay. And then we said, look, but this is with respect to one particular hash functions, right? For one counter, this is with like, now we are doing with respect to, like, this is with respect to one particular counter we did. But what are we storing here? Xi tilde, what you are storing is minimum over, in each row there is a place where xi is stored. So this is a place where xi is stored, there is a place xi is stored, this is a place like the value in each of them, and we took minimum of this, and that is okay intuitively because each of them is an overestimate. So you better take the minimum if you want to get closer to the reality. Okay. And we said since we have D has functions that are pairwise independent, probability that minimum over L ZL minus xi, right, is greater than or equal to epsilon times xi one norm is less than or equal to 1 over 2 to the power d, and the way we chose our d, this is less than or equal to delta. Okay. So this is basically the proof. It is not very hard proof. I mean, this is like something very simple. Okay. And then we said, look, but this only tells you, this is a proof of this particular lemma, that for one particular index, right, for one particular index, we can give an upper bound on delta using this. Okay, very simple. But if you wanted simultaneously to achieve that each of these xi's are within the interval, within the range, right, then just these many hash functions are not good enough. Okay. Then we say, oh, now we need to apply union bound, then we need to show that, well, this is not less than only half, but this is less than some polynomial function, right? And to do that, we need to apply, like, so this is less than some polynomial function. So if I want to apply this to some polynomial function, then what did I choose? 2 power d is less than delta. So if I want this is less than 1 over poly n or something, then I need to choose d accordingly. So then you have to choose d equal to some 2 ln n and work with same w equal to 2 over epsilon, and if you use that, then you can show that by union bound not only this particular, for each I xi tilde is between, if you apply d equal to 2 ln n, w equal to 2 over epsilon, then you say for each I xi tilde is between xi and xi plus epsilon times 1 norm with high probability. Okay. Right. So if you wanted to succeed for everyone, then you have to multiply with log n in these space uses. Okay. So let me first, so this is what count min sketch is. If you have any question, you can ask me now before we do some applications of count min sketch. Okay, so let me do first what I want to do. So before I do heavy hitters, let me do range queries because that is slightly more cleaner to present. Okay. So I'm going to rub this part. So what I want to do, so these streams are coming, and for now let's just assume, just for our understanding purposes, that you only have all these deltas are positive, so that summation of xi and this deltas are positive and this like +1. Okay, so this index increased by +1, this index increased by plus just this one, so that at the end the total sum is m. I mean, it wouldn't change anything, but just for our own understanding, let's just assume that delta t is +1. Okay, you will see that nothing would change in our analysis. But now what are we interested in? Okay, so this is what we are interested in. What is called, so we are interested in range queries. So what I mean by this, so you're given I comma j in 1 to n, and you need to output me what? Summation k between I and j xk. So I want the sum of all the frequencies between the range ij. Right? So for example, I mean, why it is useful, because a lot of databases are stored like that, and you want all the object between this and this, like frequency of that. Or lot of IP addresses are between some range, and you want all the frequency of all the hits between this and this range. Okay, I mean, that is enough of motivation for range queries. Okay, so what you have to do is that, look, how many queries are possible at the end of like I have run my stream on m objects. At the end I would like to do this range queries. Okay, but how many range queries are there? N square range queries are there. Okay. 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 So I want my sketch to be done, and after that, when you give me this, I want to answer that as quickly as possible. Of course, on the way, I want as quick. So there are 3 questions, right? Quickly, space efficiently, and is there any other parameter that we need to worry about?
Less error.
Hmm?
Less error.
Less error, yes. Accuracy. So fine, I have maintained all this, but what is the problem? I want range queries also to be at most epsilon times the norm of whole thing. There is no way I can. So what is a naive way of doing this? What would have been a naive way of doing this? What would have been a naive way of doing this? Like, forget about this, I just like quickly or whatever it is, forget. I want to know what is a naive way of giving this estimate on this, n cross n table. Oh, you are saying that you keep a data structure for each ij. Okay, fine. So this is one possible answer. So keep n times n matrix and store. Okay, this. Okay, fine. How we are going to store? So we are going to store what?
For each query I store the sum. So that will be.
No. Look, we are doing all this in the streaming setting. Okay, I have like things are coming, so all you can like, so you, look.
Query is coming
Queries will be given to you later. You do not. So I first streamed some objects. I want to make a data structure that which will tell me that okay, if I told you between ij in this particular stream, what was the frequency, right? There are n square queries for this. It's not any arbitrary object, right? Like otherwise you are given an array and then you do all this, perform all these operations, right? But here I'm telling you these numbers are coming in the stream, like the 1 to n are coming in the stream, right? And I don't know, the stream length is m. At the end, I want to maintain some data structure. After the stream has gone, I would have kept enough information that from that I can create a data structure such that if you ask me, give me this query, then I'm able to support this. Or and as quickly, good accuracy and everything.
We just maintain the table from I to k. When the k plus 1 element comes, we just add it to all the previous things for k plus 1 and make a new column.
What is I?
For all the previous i's. Naive.
Okay. So what he is saying is that fine, yeah, I made your life easy when I said it is positive, okay, but I mean, okay, things can go all over, okay, fair enough, okay. So what he is saying that keep an array, okay, whenever a number comes, you go and add that number to what you are trying to do.
So the k plus 1 element is coming.
So what am I keeping? I'm keeping n cross n array, sorry, n cross n matrix or an array. What are you trying to keep?
N cross n matrix.
Okay, so n cross n matrix indexed by what?
I and j.
Okay, so indexed by some I and j. Okay, so what is this? Suppose this matrix is D. Dij is going to store my potential range, sum of frequency. Am I right? Okay, so when a number comes, what are you going to do?
So when the n plus 1 number is coming,
Some number has come now in the stream.
so we do it for I n plus 1.
No, no. So tell me precisely what you would like to do. I set it up now. Now tell me. I mean, like. And whenever a number comes, just I increase its frequency.
Subtract. 1 to, if you want ij, I'll take 1 to j and 1 to I minus 1. Subtract it.
Yeah. So you don't have, I mean, okay, fine. Okay, but it takes a lot of space, and that is not something which we are very happy with. This is something which Mishra-Grice algorithm cannot do. I mean, most of the time.
Something like a tree structure we maintain some
Login space.
2 raised to I bit tree also.
Lots of heuristics. Okay. Okay. So what happens if I just stored I just run this algorithm, I stored xi tilde. I mean, I will not even store xi tilde. If you notice, this xi tilde can be actually generated using this matrix. Do I need to store explicitly, or can I generate this from here? I have just maintained some counters, right? Some DW counters. I have way much smaller counter compared to the number of objects and the stream and everything, right? Like what am I telling you? What is xi tilde? Look, you are like here the space is way smaller compared to all the n cross n matrix or n size array which you are trying to tell me. But of course, it comes at a cost, right? What is the cost? So space is not a problem. It will. So I think we can also quickly answer this question. So if looking at this, suppose I knew this xi tilde was correct, I can suppose if this xi tilde was correct, I mean it was exact, forget about error and this and that, right? But this is what I'm going to give you. So if you ask me, I can give you this. What will you now? Can you, do you know a way, or can you, I mean I'm not telling you that run only on this date, like you run only on this. Maybe you would like to maintain something else simultaneously running when the when the object is coming, and keep lot more information, and then combine those information to give this. Like for example, he was storing for every index I and j, but then the answer was like order 1, like I sum this, I count these two numbers, and then I sum this. No, it was very easy the way he said, right? Order 1, but it was a space inefficient. I want a space efficient, but I'm willing to, for now, just imagine that this algorithm actually gives you correct answer. Right? This algorithm will give you correct answer. Right? But now, there are two issues. So forget about accuracy for now. So even if this algorithm gives you a correct answer, just this particular algorithm, and if I give you a range, how will you get an answer? I give you I and j, and I want you to give me an answer. How will you get me an answer? But that will take you a lot of time. Right? Space wise it is efficient, because now you're right, if this I and j are too big, right, then you have to go and count each of these xi, and that will take you a lot of time, right? So at least that paradigm is not time efficient. So what should I do? It has nothing to do with this and that, it is a very generic strategy which is applied. So imagine for yourself that this box which I am giving to you, like it is based on some stream coming, and imagine that you have a very perfect algorithm that given this stream and however you want to treat the objects, it will give you correctly these numbers, okay, for now. Then what can you do to this algorithm? Or maybe apart from this data structure, you keep some other data, like you keep some other objects also, enough objects so that when I ask you this IJ, you can quickly look into these things, combine them and give me an answer.
Store like a binary tree, like where each node stores the cumulative sum. You can go through the range and
How will I store this cumulative sum in this algorithm?
like you can look at the range I to j. You can see a node which covers a portion of I to j and another node.
Yes, but how do I make this algorithm to store this set of information that you are trying to ask me to store? Then what happens? These are hashes, so things are going at all different places. So what do you mean that there is no monotonicity here that you can utilize that to store information?
You can have a binary tree.
Okay.
All the xi's are the leaves, the xi heads, and then the nodes above will store the cumulative sum of a range of xi's. And when you get a range from I to j, you recursively go down the tree and see if a node covers a portion of I to j.
Okay.
And then if suppose it covers from I to some somewhere between I to j, some x, then you take that sum and then you go to the other node of the tree, and from x plus 1 to j, you take that sum and you add that and get the result.
Okay.
So that takes n log in space.
Yeah, that takes in log and space. Not efficient. Then why don't I just maintain an array?
Whatever space using say types.
No, what is he trying to tell you? Look, now he is trying to maintain a binary tree. Look, currently I am not giving you, look, this is very compactly stored here. So when you ask me whichever xi you want, I will give you that, right? But now you explicitly want all this, then I already gave you all this, you used all this, then you don't have to do any bind, because then you already used, either you take space wise one by one, but if you are going to take all those and store, then after that you don't have to do any binary tree, then I can do just array business and like store ij and everything. Okay, so how many of you heard of this object called dyadic intervals? Okay, so let's do some fun. Okay, so there's a notion of something called dyadic intervals. Okay, so what are dyadic intervals? Okay, so suppose I have numbers 1 to n. Okay, so let's say 1, 2, 3, 4, 5, 6, 7, 8. Okay, so my dyadic intervals are, so this is like first level, each is of size 1. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. Next are of the size 2 each, continuous. 1, 2, 3, 4, 5, 6, 7, 8. Next stage of 4. So how many levels will we have? Log n level. Now if I give you any interval a comma b, you can cover them with intervals from here with at most 2 log n intervals which are disjoint, pairwise disjoint. Okay. Given any interval between 1 to n, I can cover that interval with disjoint interval. So these are, let's call them dyadic intervals. These are my dyadic intervals which I have created for you. Okay, you can cover them by disjoint union of dyadic intervals. At most 2 log n disjoint union of dyadic intervals. Okay, prove it for yourself. I mean, this is not something which I am. Okay. Okay. So more formally, the definition is I comma j is a dyadic interval or range if j minus I plus 1 is 2 power k and 2 power k divides I minus 1. Okay, then this is called dyadic. Look, all of these satisfy this requirement. Okay, so what claim did I make? So the claim which I made, and look, what one more extra problem we had when you said that not only it was a time issue, because look, I don't have exact xi, I only have xi tilde, right? So if I just take that, then I also have an accuracy issue, right? Because I cannot say that it is epsilon times the 1 norm of x, because now these errors for each of them will just sum up. So all you can say it is n times or the range times epsilon times this. So it was not good even from that perspective. So it was not good from the accuracy perspective, it was not good from the quickly perspective, okay? But space efficient, yes, because we only kept one thing, okay? But now what we will try to do, I want to keep a dyadic tree, I want to keep this object for each of this level. So again, as you were saying, it's like a binary tree, right? And it's like, but this is a binary tree which I keep only in my head, right? I am not going to create this binary tree, okay? But what I'm going to create for each level of this binary tree, so in the base is this level, which is all consisting of intervals of singletons. In the second level, I will have all the intervals which are consisting, so this is like 2 power 0 size interval, 2 power 1 size interval, 2 power 2 times size interval, and so on and so forth, right? So 2 power log n size interval, which is the whole range, right? So this is what it is. So there are log n depth, and so I would like to keep this tree, a data structure for each of this level, and when you ask me a question, I will be able to answer that question based on this, okay? So first let's see how to create this data structure, and then we will worry about anything else, okay? So what do I would like to create this data structure? How would I go about creating this data structure, like creating an object? So for the first one, this is a data structure which I'm going to keep, okay? And for the second one, for this particular interval, I'm going to treat this interval objects. Imagine, I know which interval I am, right? I'm going to treat these as same number. After this, my domain has decreased to n by 2, 1, 1, or like whatever you want to say, like 1, 2 is like 1, 3, 4 is same object, 5, 6 is the same object, and that is just because I know which dyadic range I am, so I can treat which first object is, and I can just go and make the sum point, okay. Similarly, so I will have log n such data structure. How many such data structure? So we will have, let's call this data structure D, okay. So we have D0, D1, D log n. And what are we trying to do? So whenever a number is coming, I'm not only making changes to sum here, I'm going to change sum, and let's have a leader. So what is the leader for each of these guys? The leader of each of these guys, let's say the first element, right? So what I decide, suppose now I have lot of this big data structure, which, or the counter data structure. What I'm going to store in this counter data structure, okay, now some element has come. In the first I said, hey, wherever these guys are there, please go and increment this, okay. I will do the same thing. I will say, okay, now I look at this number has come, who is my leader, okay. My leader is, I can just know by looking at this, oh, now go to my leader and increment my value to the leaders in each of this, and then that's it, right. So everywhere I have a notion of a leader, so I go here, 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 and leader, okay. So that's all that I do. So for example, in the second data structure, for when 2 comes, I will go and count its sum not at HLI, not HL2, but HL1 at every places in the second data structure. Third data structure, well, again with 1, right, so on and so forth, right. And for the last data structure, we are it's just one number actually, because everybody is going to just hash to the same object, right, because there's only one, right. So this is how we are going to store this data structure, okay. Now how are we going to, I mean, we should apply this lemma in a way that we are in control of error, okay. Look, what is the property of each of these numbers? If you look at here, let D be this, let W be greater than or equal to 2 by epsilon, right. Xi is x tilde, then probability that xi tilde is more than this one norm is strictly less than tilde, right. I have mapped it, but I have mapped to that, but if I do my error calculation is always with respect to m, where m is the sum of all the numbers, right. So the property which we have here is that I just treat that as like I have made errors here, sure, because I have gone and put my number somewhere else, but if I do my analysis for the calculation, again I will get it that it is with respect to summation x, which is again with respect to my one norm. So here each of these objects are error with respect to one norm. Again, this sum is an error with respect to one norm. This sum is an error with respect to one norm, and so on and so forth. Now, if we are able, what did we say? Oh, for any interval, I need to just sum up some 2 log n objects. It means I am going to only make error 2 log n times. So if I choose my epsilon prime accordingly, or that I do not make that much error, or I allow myself to make that much error because I have chosen things much more better here, then I'm perfectly fine. Okay, so this is the whole idea of this keeping this data structure, is that we maintain this amazing data structure, right, which keeps this. To each data structure we apply this particular lemma, right, which tells us that each entry in this data structure is within epsilon times 1 range, and epsilon you have to specify, right. And now because number of times you are going to add these numbers is only going to be epsilon times some error, this is very fine. Okay. Now given this d0 d1 log n, how will you, so I gave you a range AB, okay. You can find a partition of AB into this 2 log n interval, which is there. Now once you have this, you go to each of these leader, take that sum and give me, right. So I am space efficient because I have kept only these many, and I am less error also because I will only err log n times error. Okay, so okay, so you wanted epsilon, right? So now I have to run this algorithm with different epsilon prime. So what should be my epsilon prime? Epsilon by log n, right? Because what are you going to do? You are going to sum up some 2 log n numbers, right? And each of them is going, so now I know that my error will be like epsilon prime times log n times, right? Epsilon prime times log n times 1 norm, right? Because you are going to count 2 log. But hey, but I wanted this whole sum to be less than epsilon times 1 norm. But now what is my epsilon prime? Is epsilon by log n. So this, but then W is more than 2 times epsilon prime, right? So now dW will have another log n term here, right? So that's perfectly fine. Okay. Now, are you getting the ideas? Right? I'm not going to write complete details, but this is how, I mean, this is how the ideas are. So what is clear is that if I apply this lemma for each of the counters here we count, the error is in epsilon 1 norm of this, whatever that epsilon I apply to. Okay, that's the first thing. Second thing, when you give me a range, I'm only add some 2 log n numbers. So error of these 2 log n numbers is going to add up to my estimate. To counter that, I have run this min sketch algorithm with epsilon prime, which is way smaller than epsilon that I wanted to have. Right now, there is no rocket science happening here. Okay, so epsilon prime will be like epsilon times 2 log n, apply, or 2 epsilon by log n. No, we haven't got it, so 2 log n, right? So this is epsilon prime which you will apply, and so how much space will it take? Right? But we also have to look, but not look. So this is with respect to one particular interval. We want the queries to be correct for all queries, right? So as before, we need to say we have to apply union bound and everything. So you have to also apply epsilon prime is epsilon by 2 log n. D prime we will apply is how much D prime will be, what will be D? D will be, we don't have any delta, so it's like you choose something like order log n. So what will this imply? That look, error probability was like 1 over 2 power d. So rather than writing a delta, let's write it 1 over 2 power d. And you chose like 1 over 2 power d. So if I choose d equal to 2 log n, my error probability is 1 over n square. But that is all. I mean, you choose 10 log n for all that you care. If you do, then it is like 1 over n to the power 10, and there are only n square queries. So total error, all this will occur is like 1 over n to the power 8. So with probability 1 minus 1 by n to the power 8, each of them gives you this with very high probability. Okay. Now, so this is about range queries. Okay. Now, so what we didn't show. Okay. So this is what the notion of Dideric intervals are. So the claim which we didn't do is the following. Let's see. Let me give you some.
How are you storing the dyadic interval data structure?
I'm not storing. I'm just keeping those D1 to D login. That's all my data structure is. Now you give me an interval. I know how to break it down into 2 login intervals, dyadic interval. For each of these dyadic intervals, I have a number stored and these are disjoint. I take those numbers, sum them up and give you.
So when you say I know how to make it in two login dyadic intervals, that also would that you if I have this key, then I can do a binary search kind of thing to get the two login dyadic intervals. Otherwise, how do you know?
So you have this tree in your mind, so you can get that. It was fixed, right?
N is fixed.
And this partition, all that is fixed.
You know what these dyadic intervals are. It's just that given all I have to give you is an algorithm which given A and B produces these intervals in time proportional to the size of this interval, like number of intervals with partitions. Then I'm good. The dyadic, what are dyadic intervals? They are fixed object. I gave you a very fixed definition. For 1 to n, what is this? A range if j minus I plus 1 is some 2 power k for k between 1 to log n and 2 power k divides I minus 1. This is fixed object. So such intervals are like fixed in my head. Now how do you get dyadic intervals? So what is my claim? Yes, tell me.
So when you are saying that for the in this hash table D1 to D login, we are storing it at the leader. So do you mean that the hash functions are now from n to w, or are we doing it by n by I to w?
No, it is n to w. But I just treat all the elements in this as same object. I am not using different. Then if I use different set of hash function, I will even incur more cost. I don't want, I mean, it is not much, but I mean, it's just some another polylogin, but we don't. But look, I mean, if it makes sense, I mean, this are nothing. I mean, you can run this algorithm at different levels, completely different. So whenever streams are same, but the implementation of these algorithms are different. Right? You can use like completely independent hash function in each of them. You can use them. It wouldn't hurt us. Like it is just some polylogin extra space. Right? So even with all this, to all this we are multiplying with some polylogin here, some polylogin here, which is perfectly fine.
Not use different new hash functions.
They are independent for these objects, no?
No, because when you are finding the range by taking some things from different DI matrices, and then for this calculation you need it to be independent, right? So if you are using the same hash function, they are not independent.
You can't do union mode simply. The union mode which you did, you can't do which is
Why can't I do?
because you can't simply multiply the one minus that term, like you did 1 by n raised to or to 1 by n raised to.
But my question is, why can't we do it?
Because they are not independent.
What is not independent?
The probabilities of
For?
error.
Union bind works irrespective of independence or dependence. For each of them, this is an error. Look, if you feel comfortable taking them, because I have not done the computation to show you exactly why it is, but if you feel that way comfortable, you can do that way, that's perfectly fine. It will just not add much to it. But I mean, you really don't require it. But you can do it, it's just a matter of just order log and extra bit. Every range ij can be expressed as at most 2 log n can be expressed as disjoint union of, it is important that they are disjoint union of at most 2 log n dyadic intervals. See, the point is if you have any interval, there is big range which is sitting inside. Like, I mean, there will be, like, the only reason why it doesn't, I mean, why you need 2 log n is that for every level you might have one extra element being left from here or there, right? So for those you might have to use these singletons. So look, there is always, there is all, look, I have something, right? Imagine yourself, like I have some range. If I have range of nature 1, 2, 3 or like 4 length range, then definitely there is some 2 size object which will be inserted, right? And so every time the leftovers from down will be, so okay, I start with singletons, now let's merge them, right? So every time if I can merge them, I merge them with something bigger, right? If I can merge 2 intervals with some dyadic interval, then I merge them, because every time, so why am I not able to merge them anymore? Because they are intervals, so they are continuous objects. So now 2 continuous objects are not able, we are not able, so now these 2 continuous objects, if I put them, they are not part of some, like they are not part of exactly some dyadic interval. This is why we are not able to do it. But then only half of them, for that half you have already used something. So if you write some recurrences, so this is like, this I have put it in exercise and I am not going to do it. This is something which you should be able to do it. Okay. So this was about range queries, okay. Now let's do what we are more interested in is in what is the notion of heavy hitters in this setting. Okay. So what is the notion of heavy hitters in this setting, okay? Let's keep this because we might need this. Okay. So I told you how to do point queries, how to do range queries, and let's do how to do heavy hitters. Okay. So what are heavy hitters in this setting? So find all items I such that xi one norm some alpha times xi for some fixed alpha in 0 1. So I want to output all those indices, all the value of xi's such that their one norm is hard. But and what will an approximate version of this is that, well, I don't know how to do this, but what I can output you any I so that xi is greater than equal to alpha minus some epsilon times 1 norm. So you are definitely outputting heavy hitters, but you may output something more. Okay. So if you believe that S alpha is all heavy hitter, then you notice that what we are going to output is like all the objects which are and which is contained inside this. Okay. Can we do this? Any naive algorithm. look, we have a guarantee on each of xi tilde that they belong to this and this if we use a log n extra factor here. So what happens if I just go through each of them and go for each I and check if xi tilde is greater than alpha minus epsilon time 1 norm and return. So what I do? So for each I, if xi tilde is greater than equal to one norm, return. Does it have all this? This has all the property which we wanted. That whatever we are going to output definitely has this property, because what is the property of xi tilde? Is that xi tilde are at least greater than equal to xi, right? But they are upper bounded by 1 norm. So if I output all those terms here, I definitely output all those which are in alpha minus epsilon because of this inequality, right? Because what I'm outputting an xi tilde whose value is this. So its value could be anything between this and this. So for sure we are outputting all those elements whose we may not be outputting. This is why I wrote S. We are outputting is, so for any I which will output will have property that at least this happens, right? And now because S alpha is contained, but it may not be giving you S alpha minus epsilon. What I am going to output will not give you everything in S alpha minus epsilon, but it is guaranteed to give you everything which is in S alpha because of this inequality, right? Because any number which I have output this, right? But it could be very close to this number for all that I know. Okay, but how much time it will it take? How much time it takes? N. Okay, how much time does it take to output one xi delta? It is proportional to the table, no? Because I have to find min of all this. So it's actually it will end up taking order n log n time. Because to output each of these guys, you need log n time. Because how will you say, okay, I look at my box, go through each of these numbers, and you have to output p minimum, no? From all this. All I have is this count data structure, right? I have to go through each of these rows, and because we want to succeed for everything, my it's like log. Right? So this is very bad algorithm. I mean, so how can we do better? Do you get my question? Right? The way we did it for range queries, I would like to do something for here. How will I go about doing it? Look, you have to keep some tree in head, and you should be able to traverse that tree without going through, without keeping the tree, what do you call, explicitly. Okay, forget about this. I mean, how will you go about keeping some sort of data, like some sort of tree-like structure that you can use that to output these kind of objects, and then we will see how to do that in an implicit way. So we can view this dyadic tree as a complete binary tree with one node having two children, okay. What should, look here, last time you had some meaning of this, you kept something. What was that? What did it keep for all this? Summation of, yeah, so so think of this as a, forget about like alpha and x. Suppose this was m and we were doing, I want to output all the element with some m by k. How it will do? Look, total sum is m, right? Total sum is m. Then is it possible that, and I want to output all these numbers more than m. So is it possible that if I sum the frequency of all these guys here and sum the frequency of all these guys here, both will be less than m by k? Is it possible? What is, like, suppose for an interval I comma j, I, let fi be the sum of xi, xk in the interval, okay. So let us call this frequency of the interval or whatever you want to call it, okay. And suppose they all were positive and sum is m. Is it possible that the whole frequency here is more than m by k because this is m? Is it possible that these two child will have value less than m by k? No. Okay. But if it has value less than m by k, what does it mean? It definitely does not have any xi whose frequency will be too much. So I should just follow my child wherever my child takes me to. I ask myself, what is the sum of your frequency? It tells me m. Okay. I look at my children, I ask, what is your frequency and your frequency? If it is more than m by k, I follow those children. So I follow this child. Then I ask his children, right? So I am trying to do BFS on this tree with this. So I ask, what is the frequency of my children? If it is more than m by k, then I follow, otherwise I just cut it. I said no more, I am not going to traverse this tree. Because this itself, the sum of many objects is not greater than or equal to m by k. How can there can be an element with frequency more than m by k? Okay, fine. Then you go here. Then you go here, right? So how many such element will be there? Roughly like order 1 over alpha, right? So if we can do this binary tree business nicely, we will be happy. But again, there is some error and this, so you have to be bit careful. So again, what we can do, like before, we can just keep the count min sketch for each of these intervals, right? For each of these dyadic intervals, I can keep my count min sketch, which tells me whether the frequency is this or not. So that looking at this, I can just quickly look at this and say, hey, if I know my what child are in this tree, right? Because they are dyadic intervals, right? And for each dyadic interval, I have the sum of their frequency stored in one of the buckets, right? So as before, I will have log n different count min sketch algorithm running it for each interval, and what are they storing? They are storing the frequency of the intervals. This is exactly what we stored last time. So we will again have d0, d1, d log n, and now how will I do my binary search? Okay, so fine, let's look at this guy. What is d log n tells me about this interval? Because now among this interval 1 to n, I have to output everything. Oh, it tells me that this frequency is some m, like, or some m plus some errors. And now we have to again control the error, because now when you go to the second, that sum is also with respect to some error. You go there, that sum is also with respect to some error. And this is why we are not able to do exactly, and we are doing alpha minus epsilon, right? So you will run again these algorithms with epsilon by choosing epsilon prime by is equal to some epsilon by 2 log n and things like that, okay? But what is my algorithm? Now I have this, so forget about this. So now I ask this sum, this is sum. So now I ask is 2 children. I know who are my 2 children are, like just split in the middle. I know my children. For any interval, who are its children? Split in the middle, right? And apply this interval. So you know who our children are, then you can go and check, right? So now I'm running this BFS tree or BFS tree, I'm running this BFS tree, and I stop this BFS tree when the moment it tells me, oh, this child does not have these many, right? And I just keep running through. And whenever at the end, when I get these leaves, I return you those leaves as potential S. What is the space taken by this algorithm? Look, total number of leaves you will ever reach is like some order 1 over alpha, right? And this tree has depth at most log n. So each from leaf to root path, right, covers all the guys which we have ever encountered. So some order log n times 1 over alpha, right? So I'm running this tree, BFS tree, on this, but without having this stored. So, but now what I have stored, this D0, D1 to Dm. Right? So I just ask, are you heavy? He said yes. Then I ask my children, are you heavy? If some children say I'm not heavy, I said okay, let's not go further, because if this is not heavy, then there's no way this subtree will have an element which is heavy. Fine. So I go to the subtree which is heavy. Fine. I ask question, oh, both of my children are heavy. I should proceed both. This is why I said it's a BFS, but with a, what is that called, modified BFS. I'm not running completely on that tree, and I ask myself every time, if not, then I don't move, right? And when whichever will go and reach at the end, those all objects will be your S alpha minus epsilon objects. Now, how many leaves are here? Some leaves which you returned correctly, and there are some leaves where you just stopped, right? Show that is also not too many, then we are happy that the total amount of space this particular algorithm would have taken is proportional to the size of this tree, right? Because I am not doing anything more, right? But for each of this, you can charge to one of these guys, right? Each times you can, no node will be charged more than once, because look, charge it to its parent. For each leaf, charge it to its parents. No parent will be charged more than once, because every parent has just 2 leaves. So maybe 2 times. Every parent will be charged 2 times in this tree. That's it. So doing this, we can output all S alpha minus epsilon, right? And again, you have to apply with epsilon prime with epsilon 2 log n. So what are we learning now? When we were doing just normal data structures in our algorithms, we were just worried about space and this. We never worried about accuracy. But now, because of this accuracy, you have to also worry about some other set of things. Okay. So if you remembered our randomized algorithm course, we did Bloom filter. Wasn't the Bloom filter exactly same thing? So actually, we can create Bloom filter using min sketch, count min sketch. Okay. So I have last 5-6 minutes left. We'll do more application next time, but after doing one more algorithm for this. But first and more basic question: why is this algorithm a sketch? I told you what the meaning of sketch is. There's a matrix, there's a vector, and we should be able to do this. Why is that? because I don't think we can do sparse recovery today. So, as an application, okay. So, let us see why it is a. So, what we need, if I want to think of this like I need a matrix such that, and my current is like x1, x2, xn, and to get an updated thing I should be able to multiply with this matrix. Think of this as a vector of certain dimension, this vector as certain dimension, and we should be able to do it. Okay. So, what did we do? So, our general D matrix was, if you remember, there was like L1 to D hash function, H1, H2, HT, HL, and here we had 1 to W, the ranges. But we knew that each HI has a range 1 to N to this. So, that N is there with us. Okay. And what was CLS? We said it is I, all those hash function L, all those such that HL of I is equal to S, right, Xi. This is what it was. So, thus once hash function is fixed, I would like to write it CLS as some vector times x, some u dot x. Okay. This is what my whole object. If I can write this, then I know which matrix are we talking about. Okay. So, what do you think is a possible u you could think of so that u dot x is exactly this number? Hmm?
Say it's a 0, 1 vector with
With what? So, for look what I am doing now, for each counter I am writing a vector. So, what will this matrix will be? What will the size of this matrix? What is the size of this matrix? dW, right? So, this matrix size will be dW times n, right? For each entry I am going to write a vector. Hey, come on, this is obvious. Now that I have told you what this whole thing is, for each entry I have a row. It's a 0 n vector, whichever index maps to S, put it 1, 0 otherwise, okay. So, u is in 0 comma 1 to n, where ui is 1 if and only if HL of I is equal to S, right. So, all those indexes where this I is 1, I have put 1, right, all other places 0. So, now if you multiply this column and this, where it will take some 1 into the x size, that is it. So, this is exactly what it is. So, this is a matrix. Now, and this matrix just depends on this H, right. So, once I have H, I know how this matrix is, right. So, now whenever this x comes and whenever new I delta comes, can't I update this x size just by looking at these things? So, this is why you should think of this as like this is your M matrix, this is a matrix M. So, now if you think, this is why you are able to do negative, this, right, positive updates, because this is a linear matrix, right? And everything is like Mx. Okay. Okay. So, what is the plan for the next week is do sparse recovery as an application of count-min sketch, but this is a data structure in itself, and then we will do what is called count sketch, which is again to do all these things you can do these things, but the error which we were getting is like epsilon times 1 norm will get epsilon times 2 norm. Okay. And there we will, why it is called count sketch, because there we really don't try to overestimate, we also try to delete things so that things are in much more tighter condition. Okay, I think I'll stop.